about how to explain things to people outside of our field, or in fact to non-mathematicians. And we don't compare mathematicians to each other, certainly not. So I searched for a metaphor, and it's basically he's a prize fighter with a 20-0 record, and it's 20 knockouts. That's what it is. I've heard his work characterized as starting with really subtle, surprising points, and then building, grand edifices. He's a theory builder, but always motivated by some big, outstanding problem. He always manages to kill it. It's a knockout every time. Zlil's a deep thinker, his vision, tremendous creativity, technical power. He's made everything much more interesting for everyone here. For the past 30 years, I've witnessed 25. I was a student at Princeton when he was a instructor, a postdoc over there, and I knew that he was an amazing person. Even I realized it then. The field has basically consisted 30 years of Zlil doing something, and then 5 to 10 years of waves and aftershocks of people digesting his work and responding to it. It is not. It's a statement of reality. I'm looking at some of our friends who know it. The isomorphism problem for hyperbolic groups, the Hopf problem. He introduced JSJ decompositions into group theory. His grand work, solution of Tarski's problems, established profound connections between geometric group theory and logic. We heard Tuesday about just something that he's done recently with Koji Fujiwara. Beautiful, definitive work on growth in hyperbolic groups. Again, knockout blow. So the topic today is model theory over groups. He's going to survey and tell us about some of his celebrated contributions. So thank you very much. I'll pass this.
Okay, so first, thank you very much. Well, definitely for this introduction. And yeah, what I chose to do is to give really a survey of results between model theory and groups. Actually, I thought I actually spent probably half of my career in this direction, and I got into it as Danny just mentioned. Although I wasn't a student then, I was a postdoc, but Rips, who was my advisor, convinced me to get into that. In fact, this was a marvelous intuition of his. He thought that, I introduced the JSJ then back, was, I don't know, 93, 94, and he thought that the JSJ may be the key to this subject, and indeed, the JSJ now, it originates from three-dimensional anthropology. It moved to groups, but apparently it is fundamentally in logic. I used to think that afterwards that the JSJ was discovered by topologists, perhaps for a reason, but if not, then logicians should have discovered that probably later, although it would have been much more difficult. But it is fundamentally logic, or anyway, in the area between model theory and group theory, in some sense not less than it is fundamental in low-dimensional topology. Okay, I won't talk that much about this connection, but that's how I got to that, and I think the JSJ now is really essential there. As I said, what I'll do is mainly survey. I will also put in light some results which I think are less known, and for me they're still quite mysterious. I also thought that maybe others will take them, and I think they are just the beginning of things that maybe will flourish afterwards, and also will give explanation to them. So I hope to get to that. But I'll start from the very beginning. Okay, I assume that many here don't have any background in logic. We'll start with what is modern theory of a group. So what's the beginning? So the beginning is sentences and formulas over groups, or over algebraic objects more generally. And over groups, okay, the operation that we have is just operation in groups. We have equalities and inequalities. And a sentence will be just something like, okay, for any x1, there exists x2, etc. Finitely many quantifiers like this. In general, because the number of variables is finite, but not necessarily one. And then, okay, we use the operation in the algebraic object. So in groups, okay, we have a system of equation, which just means basically words in the free group generated by the variables, so words equal to one, and other words that are not equal to one, and a finite disjunction of such. Okay, and okay, this is always the beginning of a first order theory. Or I should say, this is a sentence, and a formula that defines a definable set is the same thing, but now we have free variables which are not under the quantifiers, and here each system of equation contains the variables which are under the quantifiers plus these free variables. And again, in general, there are finitely many of them. It's not one. It's the same thing, and we ask what values of these free variables actually the corresponding sentence. Okay, now after we give value to these free variables, this becomes a sentence. So the sentence is a true sentence, and this will be the definable set. And the structure, the question is what can one say about the structure of this set, of these sets, and other questions, you know. Okay, then there's a long way of properties of the first order theory of the algebraic object, but you know, one of the first questions that one asks also historically is what is the power of first order theory in distinguishing algebraic object. So it means that if we have two algebraic objects, in our case it's a group, but it doesn't have to be, okay, and we know that they have the same first order theory, namely, you know, the sentence here doesn't use elements from the group as I wrote it. We could use, I mean, we can look at sentences that use elements from the group, but if it doesn't, then it makes sense over any group. And we say the two groups are elementarily equivalent if any sentence which is true on one is true also on the other, and vice versa. And the expressiveness of the theory is, well, suppose we know the two groups in our case, okay? Two groups have the same first order theory, so has the same collection of sentences that are true and the same collection of sentences that are false. What can one say about their algebraic structure? In general, they need not be isomorphic, but what's the connection between the algebraic structure? And there are general theorems that will say that, you know, if you have this is called a model for the theory, in some power, then there will be other models in higher powers. But for us, okay, we again for this talk, I'll always concentrate on finitely generated groups. So this is finitely generated is not exactly a model theoretic assumption, but we will concentrate on that. Partly because then, as it turns out, there's a lot of geometry into this question. There's a lot of geometry behind these problems. Okay, so let me give first some very basic example for the expressiveness of first order theory. So the first examples that are very easy to understand are finite groups. So, you know, finite groups, one can encode basically the multiplication table by these sentences, and therefore, if two finite groups have the same first order theorem in general, if another group has the same first order theory as a finite group, then it just have to be this finite group. Okay, you can express if it's a finite group, you can express the number of elements in the group as a first order sentence. So immediately it must have the same number of elements, but actually you can interpret or express all the multiplication table of the finite group using the sentences. So finite groups, if they have the same first order theory, they have to be isomorphic. Okay, this is a very easy example. Okay, let me give another easy example. Is finitely generated abelian groups. Okay, so we have the basic structure of finitely generated abelian groups, and it's not very difficult to see. Let me just say, okay, let's take the free abelian groups, finitely generated free abelian groups. Then one can look at mod 2, at the elements mod 2. then it becomes, okay, there are only finitely many classes mod 2, and these classes can be counted using this, using these sentences, first order sentences. So therefore, it's also the same conclusion. Okay, if two finitely generate abelian groups, or actually in general, if you have a finitely generate abelian group and another finitely generate group that have the same first order theory as this finitely generate abelian group, then they have to be isomorphic. And actually, for abelian groups in general, without the finite generation, there's a complete classification of when two groups have the same. Abelian is also a first order theory. So when a group is elementarily equivalent to a finitely generate abelian group, or to a abelian group in general. Okay, let me go to another example, and this is an important group. Here already there's a phenomena that one doesn't meet before. So currently two nilpotent groups N1 and N2. Okay, if they have the same first order theory, they need not be isomorphic. There are examples like this, but okay, if you look at the direct sum with Z, with the infinite cyclic group, then they are. So this is necessary and sufficient condition for finitely generated nilpotent groups to be to have the same first order theory. It's not very far from isomorphism, but it's not isomorphism. Okay, that's there are examples like this. I will not get into that. To get closer to what I want to talk about, let me move to another class, not groups. So if one looks at finitely generated free semigroups, okay, let's say Fsn, okay, with n generators, but only the positive words. Okay, then it's not difficult to see that one can count by these sentences. One can count the how many generators this free semigroup has, because these are precisely the elements that are cannot be expressed as actual products. It's a product of non-trivial elements inside the free semigroup. So you can really count the number of generators. Therefore, if two free semigroups are elementarily equivalent, then it implies immediately that n is equal to m, and they are isomorphic. Okay, so this immediately says that at least among free semigroups, first order theory can distinguish them. But you see, the fact that this problem is easy doesn't mean that the theory is easy, because this is a very old theorem, maybe well known in some circles, of Quine, who was actually a philosopher, but was interested in that because he was interested in philosophy of language, and he was influenced by Tarski from 1945. Okay, it's not a difficult theorem, but it's an important one. He showed that arithmetic can be interpreted in the theory here. The arithmetic of the natural number, of the integers can be interpreted here. And that means that Gödel incompleteness theorem applies for this theory. And the integers as a ring, not as a group. Okay, it's not, I'm not going to get into that. It's not very difficult, the theorem, but again, it's really important in a way. And what I want to start with is, see, this is just a free semigroup. And Quine actually writes in his paper that he was influenced or whatever by Tarski, and Tarski asked his famous question, what about free groups? So he gave this example. Is it true that a free group and two generators and three generators have the same first order theory? And you see there's a big difference between what happens here in semigroups or all the other cases. If you want to separate between two algebraic objects or two models in general, you just need to specify a particular sentence, or sometimes you can give a family of sentences that one of them, you can guarantee that one of them will separate them. So we give different answer on the two. If you intend to prove that two objects have the same first order theory, then you really need to understand why, if a sentence has a true answer on one object, it will have a true answer on the other object. And this means that one needs somehow to understand in a way syntactically why a sentence is true over each of the objects, and why this syntactic understanding of sentences on the two objects, if the syntactic understanding in one of the objects somehow testifies that the sentence is true, then the same syntactic proof will also work for the other. Okay, this is a completely different problem. Okay, it's not proving a rigidity of an object, but actually proving that the theories are actually the same, even though the objects are different. And then, okay, I'm going to get to that. Once you really get some sort of understanding, in fact, a geometric understanding, why a sentence is true on one or in a free group, and therefore this geometric reason will work over the other, then it turns out, okay, it wasn't expected from the beginning, that this understanding actually helps to understand not just this question, but actually helps to understand what are all the finitely generated groups that have the same theory as a free group. We completely classify them. And what appeals to me, okay, I'm going to get to that here, as I said, there's a lot of geometry behind this question. I don't think that Tarski has an idea that there's a lot of geometry behind this question. And he asked that in 45. But already to classify the groups, geometry, you really need geometry in just describing these groups. And then if you continue to study other properties of the first order theory of a free group, then not only the techniques, but actually the answers. Okay, you get into a process that the questions are in terms of model theory, in terms of logic, but the answers are all geometric. Okay, and this goes again and again, and there's no wonder. I mean, this theory is really a geometric theory, although the question and the source come from logic. Okay, so let me start talking about this problem of Tarski. Okay, let me erase this as well. Okay, I hope to just start with Tarski problem and then go to other things, but okay, we'll see what time actually allows. So the first thing, okay, we have to look at sentences. So the first thing is, okay, we can look at say F2 or in general Fn, okay, and we look only on the part of the theory that has only one quantifier. So it can be either existential or universal quantifier. Okay, and we claim that if you consider just sentences with one quantifier, these are considerably easier than general quantifiers, then it's easy to see that that sentences with one quantifier cannot distinguish between the groups. This is completely elementary, and the reason is that you know, any two free groups can be embedded one in another, and if you just ask existential question, if something is true here, just by the embedding it will be true in the image of this embedding, and again, okay, anything which is true in Fm will be in Fn. So all free groups are actually have the same or satisfy the same existential sentences. This is immediate. You know, the next thing, you know, logicians actually usually filter these sentences or formulas by the number of quantifiers, to be precise, by the number of change of quantifiers. It's not important how many variables are there any quantifiers, but the number of changes of quantifiers. And the next step will be to go to two quantifiers. And okay, there is some paper by Sacerdote from 73, but okay, it's not exactly a complete paper. Anyway, one can say something about that. This is using small constellation techniques. One can hope that you know, that one can maybe push a little further than two, but this type of approaches using small constellation techniques, this was, I think, clear even back then, cannot do things in general. Okay, they can, well, maybe do for two, maybe for you know, three, or if one will be extremely optimistic, four, but it wasn't done before, but not even for three. But this is limited to a very small number of quantifiers. You know, there's a well-known I think phrase of Tarski that I think two changes of quantifiers are already beyond the perception of human being or something. Okay, so the really in some sense fundamental theorem in this towards this theorem which is necessary and well, probably necessary at least. It's a very difficult theorem, and this is many times what one wants to achieve is quantify elimination. In this setting, it's a fairly unusual occurrence of quantify elimination, because in fact, one can always cook some artificial examples like finite graphs with incidence relation, but usually, not usually, I think it was always the case before this theorem. When you prove when cases where quantify elimination was proved, then it's quantify elimination to a very small number of quantifiers. So, like in algebraically closed field, the quantify elimination is to the Boolean algebra of varieties of sets that are defined without any quantifier free sets. And logicians usually get to sets that are in the previous example to theories where there's a quantify elimination to the Boolean algebra of one quantifier. Here, somehow sets with Boolean algebra of sets with one quantifiers are not enough. Namely, one can find sets that are that cannot be described in the Boolean algebra of set with one quantifier. Luckily, I didn't know it when I got into this project. Sasha Osborov, who worked on these problems in the 80s, actually he was an Eisenstein chair as well. But after I finished, he told me that he knew that all the time. Luckily, he never made it public, because this is really a reason to desert the problem. That's what happened to him. Because he had this example, he left the problem, and injustice. Because what can happen with something like this is like the case in set theory, that you have Borel descriptive set theory. You have Borel sets, then you look at projection. Projection is like existential quantifier. So you look at projection, you get analytic sets, and then you look at projection of analytic sets, you get new sets, and then projection of these, you get another new set. So each time I should say one should close it under Boolean combinations. Okay, so there's a famous theorem of Suslin that this hierarchy never terminates. This could have happened here as well. Okay, but luckily here, after two iterations like this, it stops. But if you know that after one time it doesn't stop, this is a very dangerous situation. And in fact, when I met Osborov before I finished this work, that was his way to know if I'm actually doing something right. He just asked me if I if I think that or to what level there is quantifier elimination, or I used to tell him that I think that I never proved it, but I think that there will be quantifier elimination to Boolean algebra of sets with one variable. For him, this was of course a signal that there's still no chance. Okay, so the theorem of quantifier elimination is that every definable set, okay, this is a set that is defined using a first order formula, is in the Boolean algebra of, okay, I'll call it AE set. So this is sets that are defined using two quantifiers. So it means that that to define a set, one actually needs three quantifiers, but it's better than that. Okay, it's not just three; it's a Boolean combination of sets with two quantifiers. Okay, but Boolean combination contain AE and EA. So if you want to describe everything, it's really three quantifiers. This is a rather difficult theorem. It took me several hundreds of pages to prove it. And let me try to explain. I mean, there are various reasons why this theorem is very difficult. But let me just try to give one reason, but one major reason, not the only, as I said, why this problem is so difficult. And it's not just that it's difficult. You can hope that okay, this is a difficult problem. It has a difficult solution, but maybe after one solves it, one understand why one can actually prove quantifier elimination. I'm not saying even to this level, but why there is quantifier elimination. And in this case, I should even say that I still don't understand, even today, okay, it's more than 20 years after, I don't really understand why one can solve this problem. There is a solution, okay, there is a proof. It's a rigorous proof, but it doesn't give any conceptual explanation why one can actually prove that. Okay, the fact that there is a proof still doesn't mean that one understands why could have found the proof. And let me try to explain one major difficulty in studying all this theory. Again, it's not the only one, but I want to try to explain that. So suppose we even look at even a sentence with not even a set, but a sentence with only two quantifiers. This doesn't involve quantifier elimination, but just that. Not equal to 1. Okay, just this is far from the general case, but let's just look at that. And we want to study such a sentence. So one can think about this. In general, one can think of first-order sentences as a game with two players in this case. Okay, because there are only two quantifiers. In general, okay, doesn't matter actually, two quantifiers. There will be two players. One is the universal, and the other one is the existential. So the existential is the player is the one who wants to prove that the sentence is true. The universal tries to fail the other one. So what he will do, he will give him particular values of y, and the other player should answer, give an x so that the sentence is true. And the universal one will try to give hard life to the other one. For this, there is a famous theorem of Merzlikov from 1966, which is just the beginning, if you want, of this game. And what Merzlikov showed, that if this sentence is true, then it's possible to, just for the equalities, not the inequalities, it's possible to play systematically. Okay, that means just for the equalities though. That means to choose the x as a function of y, as a word in the y's. And what does it mean systematically? It means that if we plug it into the equations, then this will be 1 in fy. So it's identically 1. For every y, it will be 1. Okay, if it's true in the free group generated formally by the y's, it will be good for any substitution, any value of y. Okay, the problem is the inequalities. This is something that Merzlikov didn't treat at all. Okay, it makes the question completely different. Because, if you consider also inequalities, then, okay, we succeeded to answer the equalities, but what happened with the inequalities? So we plug it in. Okay, this will be some c of c hat of y, and it fails whenever it's 1, right? When it's 1, the formula that Merzlikov gave us doesn't satisfy the inequalities. This is something Merzlikov didn't do, but one can show that there is at least a single value of y for which this is not 1. In other words, it says that for generic y, it will be not 1, but there will be values of y for which it is 1. And therefore, there will be a remaining set. This is VP. Okay, this is all the y's for which, I'll just say psi of y is equal to 1. But psi of y meaning after we use this formula, which I call formal solution. Okay, so okay, now the universal player will play inside this variety. Okay, and what will happen here? So unfortunately, and this is a big unfortunate, one cannot, Merzlikov consider only in that aspect, he considered only the first step, only where this y was not restricted. But you see, now what we need is to continue playing where this is in deep C. And his formula doesn't work anymore because we used it. So we need to try to play systematically for these existential variables, but when y is restricted to some variety. And it's impossible to find, there's no implicit function theorem here. It's impossible to find this existential variable as a function in the y. This is just not possible. Okay, one can give examples for something like this. However, it's possible to find something like this in a bigger variety. So there is a general form of Merzlikov theorem that Merzlikov couldn't improve it, couldn't have, well, he didn't have access to such theorems before because varieties were not understood in 1966 over free groups. This is This is it's possible now because of the work of Makanin and Rosborov. It was done in the 80s. But it's possible to prove a general form of Mesdakov theorem, to find something, however we add variables. So you see, we started, say, with all the y's. There's this VC, but now, okay, when we consider what left, okay, we plug it in, so we get an equation over some bigger variety, or in some extra variables. Okay, so what left is not a variety anymore. If we consider just the y's, this is a projection of variety, or what is called the Diophantine set. And unlike, say, the complex number or something, the Diophantine sets are much more complicated than varieties. Okay, over the complex number, projection of a variety is in the Boolean algebra of varieties. Here, it's very far from being true. And not only that it's very far from being true, but so let me give you an example. They don't satisfy any descending chain condition. So it means that we can have chains we can start with one Diophantine set, and then another Diophantine set, and another Diophantine set, etc. And this never terminates. Okay, the reason is that here is a very easy example. Okay, this will be a free group. We consider in the beginning all homomorphism from F2 to F. This is the starting point of this sentence, all y's. Now, say we embed this by some embedding into F2 and consider all homomorphism that factor through this embedding. Okay, this is already a restriction. Now you can continue doing this thing, etc. And we get smaller and smaller set. Each time we require the homomorphism to factor through a finite chain here, and this never terminates. Okay, and we can make sure we can give examples where the intersection is empty. We can give example where the infinite intersection is not empty. Okay, so no descending chain exists in this theory. And there's no conceptual explanation, therefore, why we can continue with this process and it will ever terminate. Okay, what will happen is every time we are going to collect new variables, so we're getting bigger and bigger varieties with smaller and smaller projections. But what smaller means here? Okay, so this really requires a lot of work, and there's a lot of geometry behind that. And apparently one can find such a procedure that in the end give a quantified elimination. So even sentences that are not with two quantifiers, but with more quantifiers. The thing that this is very difficult is also because, in mathematical problems, if at each step, how you can take them, in a greedy algorithm, you just know that you need to optimize and go to the next step. And you're guaranteed that by doing this process, you will terminate or you will win at the end. This is a relatively easier problem, at least. Or if at each point that you are, it's clear where to go, what will be the next step? This is again kind of deterministic problem that you know how to proceed. The problem with this question is that in each step it's completely unclear how to proceed. And not only that, in order to eventually find some procedure like this, in some sense it's like resolution of singularities in algebraic geometry. In each point that you are, you have to look at all the way that you did until now and step back several steps and continue. Okay, so it's a very non-canonical, and there's not any chosen way how to go, but apparently there is a way to go. And this is what leads at the end to the solution, but it doesn't give a conceptual explanation why we could have found such a procedure. Okay, that's at least how to see why this is very difficult. Of course, after you find something like this, in a situation that it's completely unclear why there is such a procedure. When you find such a procedure like this, then it changes the situation, because then you can hope that many other things will fall as well, because in a sense you find something that was in this sense beyond the intuition before, because it doesn't have any explanation. And indeed, the other problems afterwards, other problems in logic mostly, but probably not only can use this type of solution. Again, it's not clear why the solution as itself exists, but once it exists, you can use it. Okay. Well, yeah. Happens to me before. I used much more time than I thought. Okay, maybe I'll skip some of the things that I wanted to say. Okay. Yeah. Okay. So you know, afterwards, after there is such a theorem like quantified elimination, it gives a description of definable sets, and one could have hoped that you know, other problems in logic will also be resolved, and apparently there are. Let me mention some. Oh yeah. Oh no, sorry. Yeah, that's I have to say before continuing. As I said, this gives a description. Okay, if we have any finitely generated group G, and it has the same first order theory as a free group. Anyway, after you do it, it doesn't matter what free group. It doesn't have even to be finitely generated, as long as it's non-abelian, so non-cyclic. Okay, so all of them have the same theory. After that, okay, it's a complete theory. If the sentence is true on one free group, it will be true on any other free group. So we can just say F here, and one can describe all the groups that have the same first order theory as a free group, all the finitely generated groups. It's still not known what happened if we change finitely generated, say, to countable. We still don't know what are all the groups that have the same first order theory as a free group. But okay, but let's see for finitely generated. As I said, this has what's nice is this has a complete geometric description, and I want to just explain that. So this has a tower structure, a finite tower structure, and in the bottom, what sits in general is basically a free product of I'll just denote this. This is some free group with a collection of surface groups, because you know this. Okay, and the surface groups can be either orientable or not, and the only condition on the surface group that may appear, okay, maybe there are no surface group. The surface group that may appear that okay, they should have big enough genus so that they carry a pseudo-no-sub. Okay, that's the condition, and there's a reason for that. I mean, why pseudo-no-sub comes in. I mean, it's somehow connected to this whole questions in logic. And then this is the bottom level. Okay, but there must be either a free group or at least one surface group. And then at each level, what we do is we add surfaces with boundary. Again, that carry pseudo-no-sub, orientable or not. Okay, and the surfaces, we glue them. Okay, the boundary goes to element in the previous level, and we also assume that there is a retraction from this punctured surface down to the bottom. Okay, so there is a retraction, an algebraic retraction, and you know, there could be finitely many levels like this. Each time we can assume that we add just one surface, one punctured surface. Okay, so each group like this has the same first order theory as a free group, and these are the only groups. Okay, that's the description. Let me okay, this is and again, the way that something like this is proved is first one shows that a group like this must have such structure. And then the way we argue is that we basically produce a syntactic proof over the free group, and we just argue that the proof that we produce over the free group will work also over such a geometric object. Okay, that's why it has really the same thing. Okay, let me just connect another geometric fact. Okay, it turns out that this is a theorem. It's a very nice work of two groups of people, Old Hussein. I hope I write his name correctly. Probably not. And Catherine Tent and Chloe Perrin, this is Klinos. Oh, sorry, no. I'm sorry, this is just Old Hussein. Sorry, I have to. It's just his work. Catherine Tent has other contribution. Okay, what they prove is that free groups are homogeneous. And what it means is that you know, if one looks, we have a free group, and we have the automorphism group acting on the free group. We can look at orbits. So it's clear that you know, points which are in the same orbit under the automorphism group will satisfy the same first order formulas. That's always clear, right? If you change element by automorphism, any formula, if you don't use in the formulas coefficients from the group, any formula that was true before will remain after you change things by automorphism. That's completely evident from the definition. But the question is whether elements from different orbits can satisfy the same formulas. And homogeneous in logic means that this doesn't happen. Okay, that if two elements satisfy the same first order formulas, then it means that there is automorphism to take one point to another. Okay, that the orbits under the automorphism are also okay, in logic terms, it just means that they have the same type. They satisfy the same formulas. And free group has this property. Okay, for example, primitives cannot be definable set. We cannot define them by finitely many formulas, but by infinite collection of formulas, we can define them. That's, that's a special case of this theorem. But what about surfaces? So surfaces have the same, surfaces that carry pseudo-Nusselt, they have the same first order theory as a free group. So it turns out that simple closed curves, well, non-separating simple closed curves, have the same first order theory as a primitive. We are used to the fact that many times, in many arguments, one think about simple closed curve, well, non-separating simple closed curve, as primitive in the free group. Apparently, they satisfy precisely the same, they have the same type. They satisfy precisely the same first order formulas. So in that, from logic point of view, a non-separating simple closed curve is, in that sense, analog or parallel to a primitive in a free group. But here, or let me just say it this way, surfaces are very, very far from being homogeneous. It's the model of the same theory, but this is very, very far from being homogeneous. And why is that? Because a surface, okay, let's take this surface. Here we can have, let me put it forward in the, doesn't have to be in the middle, okay, but okay, there is a retraction from the whole surface down to this punctured surface. And it turns out that this retraction, by something similar to what I described here, means that this subsurface is elementary embedded inside the whole thing. Namely, if we consider formulas just on this subsurface, and if we consider the answer inside the subsurface or in the whole surface, the answer is the same. Okay, but the fundamental group of a subsurface is a free group. It means that that any primitive in this free group, okay, satisfy also the same formulas as a primitive in a free group, which are also the same formulas as this non-separating simple closed curve. Now we know that the number of simple closed curve grows only polynomially with a length, but on the other hand, the number of primitive elements in this subsurface grows exponentially. Okay, so there are many, many more curves on the surface that satisfy the same formulas as a non-separating simple closed curve, which are the same formulas as a primitive in the free group. Okay, so surface group in that sense are very different, but actually one can classify precisely what are these curves. They are not simple, they cut themselves, but one can completely classify them. Okay, I don't have much time, so I think every time I'll decide to jump something, and I wanted to get to some theorems which I find still mysterious. And I'll jump now to talk about free products. Okay, one can go to other groups, but in particular, let me jump to free products of groups. Okay, I'll erase that. I won't need it. So free products of groups. So in free product, there was an open question which is also rather famous, probably less famous than Tarski problem. Anyway, somehow historically there were every 10 years or so, someone just in some major conference presented the major problems between algebra, between group theory and logic. The Tarski problem always appeared in the first place, but usually they more or less repeat the other questions as well. And this was a conjecture of Vogt, who was a student of Tarski in the 50s. And Vogt conjecture, okay, is again an example to how little we know or we knew about the subject. But this was always somewhat an exceptional in the other list of questions, because the other list of questions were usually on a free group or anyway in a particular class of groups. This is a question about general groups. And in general, the difficulty with such a question is that we don't know anything about the first order theory of a general. In particular, even for nilpotent groups, which are relatively simple in some sense. I mean, to work with them algebraically, or relatively simple. Already Gödel incompleteness there comes in to the theory of nilpotent groups. So, to say something about the general theory of a group, this is this is impossible, provably impossible. But still, the Voigt's conjecture, well, I don't know if it's a conjecture or a question, is the following. Suppose you have two pairs of groups, A1 and B1, and A2 and B2. And suppose we know that they have the same first order theory in pairs. Then is it true that the fact that groups are elementary equivalent preserve undertaking free product? So is it true that A1 star B1 has the same first order theory as A2 star B2? Okay, so, an attempt to answer this question, of course, one somehow need to answer this question without understanding what are the theories of the individual groups, because this is just impossible. Okay, so what one wants in an attempt to answer this question is somehow to reduce questions from the free product, from the ambient free product, down to the first order theory of the factors. Okay, that's the only possible strategy for something like this. Let me say, just as an anecdote, I just looked at that back when I worked on that. There's a very famous paper in logic by Pfefferman, Sol Pfefferman and Vogt from 1958 or 1959, and this is on generalized. I think it's called generalized product, but the meaning is really generalized direct products, not free product. And Lyndon wrote this is a very well-known paper in model theory. And Lyndon wrote the math reviews and the review on this paper. And the first thing he said is that okay, what they did has nothing to do, or doesn't shed any light on this problem. And then he actually praised the paper, which is a very good paper. But indeed, I mean, anything on direct products or generalized direct products like ultra product shed no light about free product, because it's a completely different thing. Okay, so the answer to what question is okay, let me write. The theorem is that Voigt's conjecture is true, and it's done by as I said, by reducing say a sentence or a formula from, well, a sentence, let's say, a sentence from the free product down to the factors. And on the factors, we know that any sentence is satisfied by one factor, by the first factor in the first pair. In the first pair, will be satisfied by a group in the second pair. Here, one cannot prove any quantify elimination theorem, just because, as I said, if Gödel incompleteness hold, you cannot get any quantified elimination, because arithmetic doesn't have it. However, there is some form of quantified elimination if we count only quantifiers that are over elements in the free product and not in the factors. Okay, but I will not get into that. What I want to mention, okay, in the few minutes that I have, as I said, I want to mention two theorems that I definitely didn't mean to prove, and but this was just from the proof of these things. Somehow it pops out. I mean, you cannot ignore this type of theorem as corollaries of some arguments in the proof. This is really coincidence, and they are really mysterious. So okay, I'll jump over other things, but let me mention these two theorems, which I still find, as I said, rather mysterious, and I'm sure there will be many other things if people will just get into that. So the first theorem says the following. Okay, suppose we take a group G, an arbitrary group G. Okay, there is a problem with set theory because we cannot talk about all groups, but this can be somehow avoided. You can look at all countable groups or all groups up to certain cardinality. Doesn't matter. So we take a group G, and I should say before that we fix some first order sentence phi. Okay, some sentence, and now this is fixed, and now we took an arbitrary group G. Then okay, this sentence can be true or false. Let's say it's true. Doesn't matter. One of them. And now we can look at G star G. Again, okay, it's either true or false, etc. We can look at G star G star G. And you can ask whether phi or the negation of phi holds, etc. So each time we get new groups. So the theorem says, and as I said, it's really a corollary of the tools, of the geometric tools that lead to the solution of Watt's problem, is the following: that there exists a constant that depends only on the first order formula, and it cannot be taken to be a global constant. That's easy to see. But given a sentence, there is a constant. I don't know anything about this constant, but I just know that there exists a constant. With the following property, that if the sentence is true after we take C of phi times this free product, then okay, if this implies phi, this is if and only if we continue doing this, it will remain always the same. Okay, so somehow this is stable, but stable for all groups. And the constant, again, how many times we need to get it stable, we don't know what happens before we get to this C of phi. But after we get it, that's it. It doesn't change anymore. And this has a strengthening, which is even more surprising. And as I said, I think it's just the beginning, and I also don't know anything. This is very different than all the decision problems in group theory, because this is something which is true for all groups, but depending on the sentence. Okay, so here is something which looks even stranger in some sense. Okay, suppose we fix phi again, the first order sentence. And now we look at the arbitrary sequence of groups. So this is GI, I go from 1 to infinity, but it's an arbitrary sequence. Okay, and we can look first on G1 and see whether phi holds, and then G1 star G2, etc. if phi holds, or maybe negation of phi, etc. Here we cannot expect that it will stop. I mean that the answer will stop after a bounded step, because maybe the groups that we feed this free product in the beginning doesn't make any change for the first order sentence. If you want to take an extreme example, just take in the beginning. You can assume that this doesn't happen, but just take in the beginning the identity. Then it doesn't change anything, and you just a step median, you'll start changing something. But even if you assume it's non-trivial, it doesn't matter. Maybe it doesn't. For example, if you count number of conjugacy classes of involutions, so maybe all the first groups don't have them, but you start entering them just in step 1000 or something. So you cannot expect something like that. But here the theorem says that there exists some other constant d depending on phi. Okay, so that there is some connection between the constant, but anyway, there is another constant such that the number, you cannot say where it stabilizes, but the number of sign changes, okay, along the sequence. Sign changes mean that here phi holds and here the negation of phi holds. This is a sign chain. The number of sign chain is bounded by d of phi. Okay, so for all sequences of groups, the number of sign changes is universally bounded, and the bound depend only on the sentence, not on the sequence of groups. Okay, that's and again, I have no idea what this constant is, but somehow it's a kind of universal theorem for all groups. The groups don't have to be countable or anything, just groups. Okay, all right. So I think I exhausted my time, so I'll stop here.
So actually, at the very beginning, you were talking about this, the surfaces that you're adding into the group. That the Cuba itself be supported on
the surface. On the on the surface of it.
Can't have anti-free holes.
No.
And you said that there's something on the logical side with forces.
Let me, in all this was even if let me try to explain it this way. Even in, if you go back to Mezdakov theorem and it's okay, let me just say, let's look at this sentence. Okay, this here there are no surfaces, but I want to just to try to explain what you said. As I said, one can think about it as a game between two players. Okay, and the first player want to make life hard for the second one. So the way he cannot choose any y. He just want to give him a particular y, and then the other one will play. So the way he will play is that he will, at the beginning, he will take a y which is, so to speak, complicated enough. Complicated enough meaning that, okay, it will, complicated enough can be chosen to satisfy an element in the free group that satisfies some small constellation assumption. Okay, then X will answer. Then Y would again want to choose something which is complicated in the variety, something which behaves like a generic element in the variety. Now, what happened with surfaces is that you use the pseudo-anoso, okay, in order to construct generic elements inside the surface. Actually, practically, I don't do it with pseudo-anosovs, but that's the reason why pseudo-anosov is really needed.
I was going to ask why surface have the same theory as
why surface? Okay, so this is okay. So the first the formal reason is that the way these things are proved is that there is for each first order sentence over a free group, we find a syntactic proof for this first order sentence. What? No. I don't. That's, at least I didn't work on it, and I don't, and still not know what are the axioms. No, it's not. It's also not. My work, at least, is not algorithmic. Okay, so it uses structure theory, but it produces a proof in a certain format that uses structure. If it doesn't use, if it uses, you mean?
Just don't find the proof of the group axis. Right? So you find some sort of proof.
Yes, but you can call it a certificate. Yeah. So for example, Mezdakov said that there is a formula here. So we find all the possible formulas because there's not one, and then we see what will be the set that will remain of the universal variables after we apply all the possible formulas. And then again, over these varieties, we look at all the possible formulas, etc. Okay, but using the procedure, as I said, it's not a greedy procedure, but some sort of procedure. And this gives, at the end, it gives a certificate. Okay, quite long certificate, but it will give that. And afterwards, we argue that over a surface, for example, okay, anything that any object that over a surface, this same proof will work. And in order to prove that the same thing will work, then you need something like, okay, certain automorphisms of the surfaces that will somehow, with positive entropy, really, in some sense, at least intuitively, so that generic element in the surface will look like generic element in the free group. Okay, but this can be made completely formal. This is intuitively, that's how it is.
Like that elements that are like picnic subgroup is maximum, like this, then make it picnic subgroup is maximum. What do you mean by primitive?
What do I mean by what? Oh, what is primitive element? No, primitive element in the free group. No. Okay, cyclic subgroup is also some role here, but primitive means that it can be completed to a free basis of the free group.
Oh.
This means primitive, yeah. Cyclic groups, actually, if you ask, cyclic groups can be proved using that. Cyclic groups are, beside the whole group and the trivial group, are the only subgroups which are definable inside the free group. It's also somehow conceptually, it must be so after you have this theory.
I misunderstood, but the thing that the groups built out of the surfaces are the only groups that have the same.
No, I describe what are all the finitely generated groups that have the same first order theory as the free group. It has the structure of tower. Okay, that in the beginning and in the bottom, sorry, there's maybe free group and maybe surface group, but at least one of them must appear. Surface groups, several of them. And then in each level we had the punctured surface with a retraction. This geometric description is describe all the groups that have the same, precisely all the groups that have the same first order theory as a free group. Now, why is it that requires this whole proof?
About the theorem about of quantifier elimination. So you prove the optimal result that one
In some sense, yeah.
with two pre-dependent perspectives. Would it have been easier if you tried to prove that 50 are enough, or the same proof is already produced?
Well, as I say, if 50 was the minimum, I probably wouldn't have proved that.
What I is that maybe one would settle for a theorem which is weaker. There might be a heuristic explanation of why it might cause.
You know, usually the way to prove quantified elimination, you do it by induction. So, you know, you have to get to the step where quantified elimination occurs. Like here, I wanted to prove that the Boolean algebra of 2 is enough. So to prove that, still it's enough to analyze sets that are defined using 3 quantifiers. And then you start with a sentence not sentence, formula with 3 quantifiers, and you prove that it's possible to define the same set. It's a general set, and you prove that it's definable by another formula, which is in the Boolean algebra of 2. Actually, in free products, that surprised me when I worked on it, that Boolean algebra of 2 is not enough. There's a reason for that, but I don't want to get into that. In there, what I managed to prove, or what I needed to analyze, are sets with 4 quantifiers. You know, every time you have to go further, this is a, you know, the complexity grows probably more than exponentially. This is a problem. So so in order to prove that there is a quantified elimination to the stage of 50, there's, by the way, there's certainly not a theory that I am aware of, except artificial ones, like a big enough graph will have this. You know, that we will have a finite graph, will have such a theory, but this is an artificial example. But to prove that something reduces to the 50, you'll have to analyze, you know, formulas with 51 quantifiers and somehow show that it reduces to 50. This is just no, okay. No, but no, this is no, even if you just need to go to, you know, for me, it was a great disappointment when I worked on it. It was a great disappointment. I believed for a long time that one can reduce it to the Boolean algebra of 1. And that means that you need to analyze only formulas with 2 quantifiers. When I found out that this is not enough, you know, this was almost a lost project, because there was no example also where people can actually make this reduction. It's in principle, you're almost lost. I mean, whatever you did for 2 is far from being enough. Somehow I was lucky, but you know, this is, there's no, I'm not aware, maybe, you know, I'm not that expert in studying all kinds of theories, but I'm not aware that there's a theorem that on a theory that you can prove quantified elimination to, you know, a large number, and actually the actual thing is that you can reduce to much less. It's the opposite. Logicians always try to reduce it to the minimum possible. Okay, because just think about it, just conceptually yeah, right. There is 0, right? Sorry, I don't hear you. No. There's no relationship between GI. Just a sequence of arbitrary groups. Changes meaning that maybe it was, you know, maybe it was true 100 times, and then it changes. In 101, it becomes. It's not the sentence is not true anymore, but the negation, right? Either the sentence or the negations are true. So in 101, the negation of the sentence is true. So the sentence is false. So you just count how many times it changes from true to false. This is bounded. You know, it can remain true for 1,000 steps, but then changes. You count only the number of changes. Yeah, it means that, right. It means that for any sequence like this, it becomes stable at some point. It doesn't change. After some point, it doesn't change anymore. That's actually the conclusion of that. Yeah. What for any sequence of groups? Yeah, any sequence of groups. Yeah, that's in particular, but it's stronger than that. Not just as it becomes finite, not just become finite, not just it becomes stable, but the number of times it changes is universally bounded. Yeah, it will not change anymore. Yeah. I'm not claiming that always the number, this maximum number is attained, but at most this number. Yeah, that's the theorem. No, it depends on the, it depends on the sentence. No, I don't know, this number comes, there are certain geometric objects that are associated with the sentence and with all groups. And, if one knows this geometric structure, then one can compute this constant. But I don't know. I mean, to prove it, as I said, we don't know anything about the theory of a general group, and the construction uses, since we don't understand the theory, the construction uses all sorts of compactness arguments, but they are completely not effective. I have no idea. I don't even know. It may be that these things are computable effectively, but I have no idea. You mean what? What do you mean an example? What for a particular formula? What will be? Yeah, okay. I can. Yes, I can give examples, but that's as I said. For example, if you count the conjugacy, the number of conjugacy classes of involutions, then you can give bounds on this constant. But of course, I'm cheating. I mean, that's not that's easy. Yeah, but in general, yeah, no, I don't know.
No, I'm not. I have a few questions myself, but let's move the discussions to our wine and cheese in the hallway and thank Zlil again.
Okay.